In digital images, in computer vision, we typically operate on discrete images, right? And that means we have to do two types of discretizations. First of all, we have to sample the 2D space on a regular grid. That is, we have discrete pixels at locations. You know what pixels stand for? Picture elements, okay? In the old television world, that was called PELs, also for picture elements. But computers, we have to be special, so we call them pixels. Right? So we have to pick them at specific locations. The other thing is we have to quantize each value. We don't get to have a continuous real value. We have some finite number of bits to represent that. So like we said, maybe you have 8 bits, so it'll go from 0 to 255. These days you tend to have 16-bit images or 12-bit, or depending upon the device. But the idea is that it's quantized to some level. Even though it's quantized, later we're going to tend to think of these things as floating point. And I'll tell you now that if you compute with integer images, like unsigned integer 8 bits, your code will just break. So use floating point images. So in general, especially in MATLAB, which we'll be doing a lot of, images are represented as a matrix of values, typically integer values to start with as an image. So here's Phyllis, looking as delightful as ever. And we index our matrices by, again, I and j, row and column, sometimes x going over this way and y going that way. If I say some pixel ij, it means row I, column j. If I say some pixel at xy, all right, xy, x is horizontal, so I have to go get the column that, so you'll have to swap them. And part of the problem is our math is always determined by x and y. And our computing is always determined by I and j, row and column, and that's a tension that we'll have. Sometimes we use 1D signals. 1D signals will just be an array of numbers as well. All right.